In this video, we're going to look at a few questions with regards to direct variations and rate of change and initial values. So we're going to look at understanding why a relationship is a direct variation, modeling a direct variation relationship with a table of values, a graph, or an equation. We're going to do all three, and solving problems involving direct variation relationships. Okay, so my first question. Which of the following tables of values represents a direct variation linear relationship? Remember that a direct variation relationship will pass through the origin. When your independent variable is 0, so is your dependent variable. When my independent x is equal to 0 in A, my y variable, which is my dependent variable, is 12. It's not 0. In B, when my independent variable is, when my independent variable is 0, my dependent variable is 1. In C, when my independent variable is 0, so is my y variable. So this is the answer right here. It is going to be 0, 0. It's going to be C. Now check D. My independent variable, x, doesn't actually reach 0 on this chart. But we can see that each successive number is going down by 1 in my independent variable. So I'm going to have to extend my table, for instance, to get 4, 3, 2, 1, and 0. And when I do that, my y variables, my dependent variables, are going up by 2, and up by 2, and up by 2, and up by 2, and up by 2. So as my x variable is going down and down and down towards 0, my dependent variable is going up and up and up and up and up away from 0. So most definitely D will not work either. So I always want to make sure that I do pick the right one, and in this case I most definitely have picked the right answer. Okay, and the second question we're going to look at is, again, a typical type of question you might see in an evaluation. Substitute the values x equals 0, 1, 2, and 3 into the equation y equals 6x and solve for y. So the easiest way to do this is to set up a table, which I've managed to do here. Except I didn't include enough spots, so I'm going to extend my table. So I can put in enough places. So I'm going to substitute the values of x equals 0, x equals 1, x equals 2, and x equals 3 into my table. And when I do that, I'm going to find the value of y. So we know that y is equal to 6x. Well, if x is equal to 0, that means that y is equal to 6 times 0, which equals 0. So I'm going to put 0 here. It's almost 0. It's supposed to be 0. Okay, y equals 6x when x equals 1. Then y is equal to 6 times 1. So y is equal to 6. When x is equal to 2, y is equal to 6 times 2. So y is equal to 12. And when x is equal to 3, y is equal to 6 times 3. So y is equal to 18. So now we've substituted our values of x equals 0, 1, 2, and 3 into the table, and we solved for y in each case, 0, 6, 12, 18, for my y values. So does the equation y equals 6x model a relationship with a direct variation? Explain why or why not. Well, looking back here, when my independent variable is 0, my dependent variable also gives me a value of 0. Okay, so it does appear to me that we do have a direct variation relationship here. Whatever x is, y is always going to be 6 times larger, okay, based on my equation here. So, it does model a direct variation relationship. If the independent variable is 0, so is the dependent variable. Also, the dependent variable is always 6 times greater than the independent variable. Try that word again for you. Than the independent variable. Okay, next question. Predict what a graph of the relationship between x and y in the equation y equals 6x would look like. Okay, so we're going to now draw the graph, and we're going to predict first what we think it would look like, and then we're going to draw it in. So here's my graph, or my plane anyway, my coordinate plane. Predict what a graph of the relationship between x and y in the equation y equals 6x would look like. Well, y will always be 6 times larger, 6 times greater than x. I think it might be obvious that it's going to be a linear graph. The graph will be linear and pass through the origin, pass through 0, 0. Okay, so it's going to be linear and it's going to pass through 0, 0. So I'm going to graph the data that we collected earlier in our table. So if we did start at 0, 0, when x was 0, we got y is equal to 0. When x was 1, we found that y was equal to 6, if you recall. When x is 2, y is equal to 12. When x was 3, y was equal to 18, which is right here. And you may be able to tell here that this is going to be a linear graph. So I get my ruler, my straight line. I'm going to have a straight graph that passes through all my points. And so it's definitely a linear graph. Now using this, I can also predict, it doesn't ask, but I can predict what my next couple of points would be. When x is equal to 4, y should be right here. So that would be, y would be 24. And when x is equal to 5, it's right up here, y is going to be 30. So I can extend this even further, but we can definitely see the common relationship here between our x and our y values. Y is always 6 times greater than x. So to summarize this, a direct variation is a linear relationship where the rate of change is constant and the initial value is 0. The rate of change we talked about in our lesson is also called the slope. A graph of a direct variation is a straight line relationship that passes through the origin. And this is something that's kind of useful. The equation for a direct variation can be written as y equals mx, where m is the slope or rate of change. And we saw in the example we looked at that our equation was y equals 6x. So we definitely had a direct linear relationship in our equation that we calculated and that we graphed.